Welcome to the second part of lecture 13 on graph theory. Today again we will talk about two connected graphs. We know that a graph is two connected if and only if every pair of vertices is joined by two internally disjoint paths. So, in this lecture we will learn some more necessary and sufficient condition for a graph to be two connected, and then we will show that all these conditions are equivalent. So, let us start with lecture 13. So, contents of this lecture: two connected graphs, and at the end we will try to solve some problems related to two connected graphs. So, we will start with this theorem. For a graph G with at least three vertices, the following conditions are equivalent and characterize two connected graphs. Okay. The conditions are: condition 1, G is connected and has no cut vertex. Okay. So, what is cut vertex? Cut vertex is a vertex whose removal disconnect the graph. For example, if I consider this graph, say this graph, then you can see that this is a cut vertex. This is a cut vertex because if you remove this graph, if you remove this vertex from the graph, then the graph becomes disconnected. So, this vertex is a cut vertex. The second condition, condition B, for all x y belongs to V, there are internally disjoint x y paths. This is what we proved just now, that a graph is two connected if and only for every pair of vertices there are internally disjoint paths. Condition C, for all vertices, for all pair of vertices x y belongs to V, there is a cycle through x and y. And the condition D is the minimum degree of the graph G is greater than equal to 1 and every pair of edges in G lie on a common cycles. Okay, so what does this theorem says that all these conditions are equivalent and it characterize two connected graph. Let us prove this theorem. This is a very important theorem to characterize two connected graph. So, condition 1, the graph is connected and has no cut vertex. That means, there does not exist one vertex for whose removal disconnect the graph. So, the graph is two connected graph. So, condition 1 says that the graph G is a two connected graph, because there is no cut vertex and the graph is connected. And then condition 1 implies condition 2. Condition 2 is for every pair of vertices there exist internally disjoint paths, and that is the theorem we just proved. So, A is equivalent to B. So, this is trivial. A says the graph is two connected, which implies for every pair of vertices there are internally disjoint xy paths. This is the theorem that we proved just now, and also B implies A. So, A is equivalent to B. Now, what about B equivalent to C? This is also true, because B says you take any two vertex x and y, there are internally disjoint paths between x and y. And C says that for all x y there is a cycle through x y. Now, you can see that these two are the same statement. So, the cycle containing x and y corresponds to pair of internally disjoint xy paths, right. So, C implies B, and once you have two internally disjoint paths you can get a cycle. Once you have cycle containing xy you can get two internally disjoint paths, the same condition. Now, we will prove that D implies C. So, delta G is the minimum degree. Delta G greater than equal to 1 implies that vertices x and y are not isolated. So, x and y can't be like an isolated vertex, because the minimum, then the degree of this x is 0 and degree of y is 0, but the minimum degree given of the graph is greater than 1. So, x is adjacent to at least one edge, and similarly y is also adjacent to at least one edge, or at least one vertex you can say. Suppose x is adjacent to A and y is adjacent to B. Now, we apply, so D implies C, we apply last part of D, which says that every pair of edges in G lie on a common cycle. So, apply last part of G to edges incident to x and y. So, the edges incident to x and y are these two edges. So, we will apply the condition that every pair of edges lie on a common cycle. That means, this pair of edges x a and y b, they are on a common cycle. Suppose the cycle is C. So, this is the cycle which contains these two edges. This implies there exists a cycle C through x and y, basically the same cycle C which contains the vertices x and y also. So, we proved that D implies C, right. Next, we prove that condition A and C implies D, which is non-trivial. So, condition A is that G is connected and has no cut vertex. Since G is connected, delta G is greater than equal to 1. The minimum degree has to be at least 1. So, we have proved the first part of D. The first part of D says that the minimum degree is greater than equal to 1, and then we have to prove that every pair of edges in G lie on a common cycle, right. Now, consider two edges x y and u v, and we have to prove that there exists a cycle containing these two edges. So, here is the edge x y and the other edge u v. Now, we use the expansion lemma. So, we add to G the vertex, a new vertex Z with neighbors x y and W, a new vertex with neighbors u v. So, what we do is that we add a new vertex z here with neighbor x and y, and we add another new vertex w with neighbor u and v, and call this new graph, you call it G prime. It is like the expansion lemma, not like, it is exactly the expansion lemma. Now, since G is 2 connected, by expansion lemma, G prime is also 2 connected, right. Now, so this new graph G prime, which is obtained by adding 2 new vertices z and w. See, you can think in this way, first you add z, and by expansion lemma the graph with new vertex z is 2 connected, and then with that graph again you add w, and again by the expansion lemma the graph G prime will be 2 connected. Okay. So, condition C says that for every pair there is a cycle through those 2 vertices. For every pair of vertices, if you see condition C, for all x y, or for every pair of vertices x and y, there is a cycle through x and y. So, condition C implies z and w, which are the 2 new vertices in the graph, 2 connected graph G prime. So, z and w lie on a cycle C. Okay. So, here is the cycle. The cycle is you can so this is the cycle basically. Okay. This is the cycle C, the green one is the cycle C. Now, cycle C in G prime. Since Z and W each has degree 2, C must contain the paths x, z, y. So, C must, since z is of degree 2, this cycle must contain this part x, z, y and u, w, v. The cycle must contain this path. Okay. But not the edges x, y and u, v, because C is a path through z, w. So, it can't contain the edges x, y and v, UV. Now, replacing the paths x, z, y and u, w, v in C with edges x, y and u, v respectively yield the desired cycle through UV and x, y in G. So, now in the cycle C, if I remove this path x, z, y, if I remove this path and add this edge, similarly if I remove the path v, u, w, v and add this edge in the cycle, then I get a cycle containing x, y and v, w. That is what the condition D says. That is what we have to prove, that every pair of edges. So, we took two pairs randomly x, y and u, v and every pair of edges in cycle G lie on a common cycle, and we have constructed that cycle C here. Okay. So, we have proved this theorem, this characterization theorem. Now, we talk about two problems. Say the first problem is you have to prove or disprove if P is a UV path in a two connected graph G, then there is a UV path Q that is internally disjoint from P. Okay. So, what we know is that if G is a two connected graph, then for every pair of vertices x, y, there are internally disjoint paths. That is true, but this exercise says that it is specifying one path. Say let P be a path between u and v in a two connected graph, then there exists another path q which is internally disjoint from P. So, is this true or false? Surprisingly, not surprising, this is false statement. This is false because of the fact I will explain. It is not contradicting with the first theorem that we proved. The only difference here is you can see that you are specifying one path P, and the first theorem says that if G is two connected, then between every pair of vertices U and V there are internally disjoint paths. But if you specify one path, you may not find another path which is internally disjoint from P. Let me just give an example to prove that this is false. Let me consider this graph. I hope that you understand the difference between this statement here and the statement that we proved in the theorem. So, I label this vertex A, B, C, X and Y. AY is also adjacent. Similarly, X and C are adjacent. So, basically this is K 2 3, it is a complete bipartite graph with one part is having two vertices and the other part is having three vertices. Okay. Now, I specify one AC path, let me call it P. So, one AC path is A X B Y C, and it is easy to see that this K 2 3 is two connected graph. Because you can't find a single vertex whose removal can disconnect the graph. So, K 2 3 is a two connected graph, and I specify one path between A and C. Since this is two connected, between every pair of vertices, say for example, A and C, there are two internally disjoint paths. That is true. You can see that the two internally disjoint paths are one is A X C is one path and the other path is A Y C. So, there are two internally disjoint paths between X and Y because the graph is two connected. Now, if I specify my one path to be say A X and then B Y and C, then I can't find another AC path which is internally disjoint from this path. So, there is no AC path internally disjoint from P. So, the difference, so I hope that now you understood that if you specify one path between a pair of vertices, you might not get another path which is internally disjoint from that specified path. But since the graph is two connected, here, you can always find two internally disjoint path, but you can't specify one path and then look for the another path which is internally disjoint from the other path. So, I hope that you understood this is a nice example to illustrate that you can't, given a two connected graph, you can't specify one path between a pair of vertices and then you can't ask for another path which is internally disjoint from the specified path. But in two connected graph, always you can find two internally disjoint path between every pair of vertices. That is all for today. Thank you very much.